Hi, and welcome to 8.6 Hooke's Law. Hooke's Law has to do with springs, bungee cords, anything elastic, anything that's stretchy. So, Hooke's Law basically states that the force exerted by a spring or anything elastic is equal to the spring constant times x, the distance that the spring is either stretched, as shown to the right, or compressed if you push the spring. Um, for the next couple minutes, I'm going to derive where this comes from and kind of show you in case you're a little bit confused about what exactly K is or what X is and what they have to do with F. I'll show where the equation comes from and then I'll come back here. So if you're comfortable with the equation but just want to see what the questions look like, you could skip forward a little bit until I come back to this screen. Okay, so in my example here, I'm going to talk about springs. So we'll have like a base case here where there's a spring. There's four loops, and it's attached to a block. And this is like an overhead view. This is like the side of a wall, and it's on the ground. And we're looking overhead. So it's not being stretched or compressed at all. It just looks like that. Well, what happens when we exert a force on the spring? Let's say we pull it to the right. The spring is going to stretch out, kind of like this. And what happens is as we apply a force, the spring force is going to increase. And if we stretch it even more, now it's really stretched out. You have to exert even more force in order to get it this far. And the spring is really stretched out. It really wants to go back to equilibrium. Its equilibrium was our base case over here. So this is kind of like the distance that we referred to. In the second case, we stretched it this far. This is known as x, the distance that the spring is either stretched or compressed. And as you could see, as we increase x, as we stretch out the spring more and more, the force also increases. So the force is directly related to x. That's the first idea. The second idea has to do with the spring itself. So let's say we have the same situation, same base case, and we're stretching it from the wall just like before, and then we stretch it again, and we make it like we did before, and now it's stretched out from its equilibrium position. All right, just like this here. Well, let's say we do the same thing to another spring, but this time the spring is different. And it's like a really thick spring, like almost the shocks on your car or any kind of really stiff spring. So it might look like this. Initially, it's the same length, and it's attached to the same size block. But now we are going to stretch this spring out, and it's really stiff. And it's hard to stretch out a stiffer spring. So what do you think is going to happen to the force required? Doesn't it take more force to exert the stiffer spring? So initially, we have maybe an applied force like this, and the force exerted by the spring might be like this. But now we need to exert a huge force in order to stretch this spring the same distance. So what we're saying is, the force exerted by the spring is also directly related to the stiffness of the spring. Now, how are we going to represent the stiffness of a spring? They use this letter K. They use the K called the spring constant. It describes how stiff the spring is, because not all springs are created equal. I kind of liken this or relate this K idea to the coefficient of friction. The coefficient of friction is basically a way for us to measure the roughness of a surface. Well, K is a way to measure the stiffness of a spring. It's just a variable, it's a number that's used to describe a physical quantity, either the roughness of a surface in the case of the coefficient, or the stiffness of a spring in the case of K. Okay, so that was under 5 minutes. Now let's go back to the questions. All right, so now we described that the spring constant is directly related to the force, and the distance that is stretched or compressed is also directly related to the force, and that's kind of where this equation comes from. All right, without any further ado, number one, the diagram to the right represents a spring hanging vertically that stretches 0.075 meters from when a 5 Newton block is attached to it. So this is like the equilibrium position. I was going to say from equilibrium. I was predicting what the question was going to say. Anyway, it says the spring block system is at rest in the position shown. What is the value of the spring constant? So this might throw you if you don't know what the heck a spring constant is and you're not familiar with the equation in general. Let's look at what they give us. They're telling us that the distance that the spring is stretched over here is 0.075 meters. Now, normally we write distance as a d. When we talked about gravitational potential energy, we called the distance the height above the floor. In this case, when we're talking about springs, they use an x. Why did they use an x? Well, because it's either the distance being stretched, or if you're pushing this and they're getting really close together, then it's the distance that you're compressing the spring. So it's used for both stretching and compressing. So they give us x. X is equal to 0.075 meters. Okay, now what else do they tell us? They tell us it's a 5 Newton block. So what does that mean? You should know if it says a 5 Newton anything, they're telling you the weight of the thing. So it's a 5 Newton block. The weight is 5 newtons. And they say it's at rest. Why is that important? That means that the forces are in equilibrium. There's no net force. It's a constant velocity of 0 meters per second, meaning that the forces are balanced. So they're telling you, by telling you the weight of the block, they're telling you the force in the spring, Fs. So Fs is equal to 5 newtons. Now, spring constant is kind of a weird term. We talked about it briefly when I derived the equation. They use a K to describe the spring constant. The spring constant basically says, how stiff is this spring? What kind of spring is it? Is it a really stiff spring, like a shock in a car? Or is it a really loose spring, like a slinky? Like a slinky is considered a spring. It's just, it's not very stiff. So, anyway, we're looking for K. And we have this nice equation. Hooke's law says Fs is equal to Kx. The force in a spring is equal to the spring constant times the distance it's stretched or compressed. So 5 is equal to K times 0.075. And you do the division. The spring constant is about 67 newtons, 66.7. Is it newtons? Oh, wait a second. Hold on. The force is in newtons and x is in meters. And we just divided 5 newtons divided by 0.075 meters. So what is the spring constant? It's not newtons. That's for force. The spring constant is a newton divided by a meter, or a newton per meter. That's some good units right there. All right, so the spring constant, the units are in newtons per meter. Because we could have rearranged this equation. Instead of F equals Kx, we could divide both sides by x, and we'd see that K is equal to the force divided by x. It's a ratio, and the units of which are newtons per meter. So that's where those units come from. All right, don't be confused by the spring constant. I know it's a new term, but you got to get used to it. All right, number 2. A spring has a spring constant of 35 newtons per meter. So K is equal to 35 newtons per meter. What is the minimum force required to stretch the spring 0.15 meters from its equilibrium position? So we're stretching it 15 centimeters. And they want to know what the force required to do so is. So you just do F equals Kx. F is equal to 35 newtons per meter times 0.15. And you get a force of 5.25 newtons. Okay. Number 3. The spring scale in the produce department of a supermarket stretches 0.015 meters. So X is equal to 0.015 meters. when a watermelon weighing 150 newtons is placed on the scale. So F is equal to 150 newtons, 1.5 times 10 to the 2. What is the spring constant for this spring? So they're looking for K. So you got F is equal to Kx. 150 or 1.5 times 10 to the 2 is equal to K times 0.015. So K is equal to 150 divided by 0.015. So that's 10,000 newtons per meter. That's a very stiff spring for this scale that we're talking about. So the scale doesn't move. If you've ever seen it before, it's kind of like this. Maybe it has a dial, and you have this hanging from it. This might be antiquated now. They kind of use like digital scales more. But there's a little spring in here, and it's a very stiff spring, so it doesn't have to move very far. You don't want this, like, if you put a thing of bananas on here, you don't want this to go all the way down. That's not very good. You want a pretty stiff spring in there. The point of the spring is just to make the dial rotate. So the dial can measure this distance. It's about 1.5 centimeters we're talking about, but the scale reading pops out a usable number. Anyway, that's how some old school scales work in the supermarket, if you ever see that. A vertical spring 0.2 meters long is elongated to a length of 0.527 meters when a hanging mass is attached to the bottom of the spring. Interesting. They just told us two different distances. And we've been looking at x. X is a measure of distance. So which one do we use? I don't know. Is it a guessing game? Is it a 50-50 shot? You either pick one or the other? You don't want to play that game, my friend, because you will lose every time. Neither one is x. Neither one of those numbers is x. You have to find what x is first. And I'll explain in a second. Here we go. Let's finish reading the question. It says the spring has a spring constant of 30 newtons per meter. What is the mass of the hanging mass? This is like a 3-step problem, because they're not, you'd think that, okay, they gave me x. Oh, no, sorry. They gave me the spring constant, and they're telling me some kind of distance here, so that's probably going to be x a little bit. They're telling me some information to find x at least. And I probably got to find f again, right? That's what we've been doing. But what are they asking for? The mass, and it's italicized. So we're going to have to do, at the end, we find what x is. Then we could find what f is. And we know fg is equal to mg because it's a hanging mass. So let's draw a diagram. It's a little bit confusing, but if we just draw a diagram, everything will be okay. That's the thing about physics. The best place to start is always the same thing. Draw a picture of what's going on. So here we have the original situation. It says a vertical spring 0.2 meters long is elongated to a length of 0.527 meters. So originally, the distance is 0.2 meters. Then you attach a mass to this guy. Oh, hold up. So it's just the spring by itself, right? We could do it this way. So that is a 0.2 meter spring. Now we attach something to it, and we want to know what the mass of that thing is. So we're stretching out the spring, and because there's a mass on it. Okay, now the spring is this long. I should have given myself some more. I'll write it on this side. 0.527 meters. Okay, and you know, there's a weight. Gravity's acting on this mass. So Fg, and really that we're talking about Fs. These two are in equilibrium. So if we could figure out what Fs is, we know what Fg is, and then we'll do the Fg equals mg. So again, like kind of working backwards, that's the plan. Before we get there though, what the heck is x? I just told you it's not one of those two numbers. If you guessed one of them, doesn't matter. They're both wrong. Okay, so what is x? X is the distance that the spring is stretched or compressed. We stretched it this far. this is X. So we have 5.27 minus 0.2 gives you the remainder, which is X. That's how you have to find X in that situation. They're not always going to tell you. In the previous one, they said that it stretches at 0.015. They're telling you X stretched by this far. Okay? They could ask it a different way, though. They could say it's originally 0.2, then it goes to 0.527, and they don't even ask. They didn't even ask you to find X first. They assume that you know how to do that. Anyway, if you wanted to write some kind of equation, you could say the distance is equal to the initial, or sorry, we'll do the final. The final distance the spring is minus the initial distance. So X is equal to, no, I guess it would be the initial minus the final. You know, we're just making up an equation. You could kind of just do it in your head, though, right? So, no, I'll do final minus initial. Sorry, I'm trying to figure out what would give me a positive number. It's really just you want a positive number. Okay, so it's just the difference between the two numbers, bottom line. 0.327 meters. That's this distance. Okay, so now that we know that, that's step one. Step two is to do Fs equals Kx. What is the force that is being exerted by the spring? Well, Fs is equal to K, which they tell you is 30 newtons per meter, times X, which is 0.327. So Fs, the force exerted by the spring, is 9.81 newtons. That should look familiar. Anyway, okay, so this is equal to 9.81 newtons. Now, that's not what they asked for, though. This is just the second step in a three-step problem. They asked for the mass of the hanging mass. So this spring right now is in equilibrium, but as shown, we're only drawing one force, and it's definitely not accelerating upward if it's at rest. This spring force is being balanced out by the weight of the mass. That's the thing that caused it to be stretched in the first place. And we know that Fg is equal to mg. So let me rewrite that on the other side here. Fg is equal to mg. And these two forces are equal to each other because they're balanced. It's in equilibrium. 9.81 is equal to the mass, which is what we're looking for. And we can assume we're on Earth. 9.8. Oops. If you wanted to be specific, if you look in your reference table, I know I use 9.8 a lot, but in the reference table, if you go to the hundredths place, it goes 9.81 meters per second squared. And yes, it's negative, and so is the force. The force is acting downward, so you get a negative number here, giving you a positive mass of 1 kilogram. How convenient. 9.81 divided by 9.81. Okay. Pretty tricky question, but if you could follow that, and if you need to watch it again, watch it again. If you could follow that, you really know what's going on. Okay. Number 5. Let me see if I can zoom in here. Number 5 says an unstretched spring has a length of 20 centimeters. When the spring is stretched by a force of 12 newtons, its length increases to 28 centimeters. What is the spring constant of this spring? So again, it's kind of like the previous problem where they're not outright telling you what X is. And this one's tricky as well because they're telling you the units in centimeters. So I'm going to draw the picture here. So you're exerting a force on this spring, which is pulling back on you. All right, and that makes you go from 20 centimeters to 28 centimeters. But if you want to consider the distance that it's being stretched, you have to look at the difference between these two here, and this is X. X is equal to 28 minus 20. So the difference is how far it's being stretched, 8 centimeters. Okay, knowing that, and knowing that the applied force is 12 newtons, which means the spring force, the force in the spring is also 12 newtons because now it's in equilibrium, the forces are balanced. It's not accelerating. It's just at rest there, being stretched. Now it says, what is the spring constant in the spring? So X is equal to 8 centimeters. And we want to convert this into meters. Centimeters is on top of the fraction, so we want to cancel it out, put it on the bottom. Converting into meters, 1 meter is equal to 10 to the 2 centimeters, as your reference table tells you. Or you could just go 2 places to the left, and you get 0.08 meters. So that's X. It's got to be in meters. And the force is equal to 12 newtons. Okay, so they're looking for K, and you get F is equal to Kx, 12 is equal to K times 0.08, so K is equal to 150 newtons per meter. That's your K. Now, let's say you did forget to do this step, and you just left it in centimeters. You could still technically get the question right. It's no problem. You could do that as long as you're consistent with your units. So this is still 12 newtons, but now we're calling this 8 centimeters. We forgot to change it to meters, or maybe we just want to keep it in centimeters, because you could totally do that. You divide both sides by 8. You could do that, let me say, in this case, because as long as you're consistent with your units, you would get 1.5. And then what do you think the units for this should be in order to get a correct answer? Technically, it should be a Newton per centimeter. And if you write it like this, they can't mark you wrong because you're doing some good unit analysis. Okay. But then if you try to do other stuff with this, like if you wanted to do the potential energy in a spring, everything else, you're going into joules then. That's the potential energy. And joules is in terms of meters. So you got to put it. Yeah, it's better to just put it in meters. It's best practice. Okay, number 6. The graph to the right or below represents the relationship between the force applied to a spring and the spring elongation for 4 different springs. Which spring has the greatest spring constant? Oh, interesting. So they're looking for K. Which one is the greatest? Now, what do they tell you? The axis. When you're looking at a graph, you always want to look at what each axis represents. So this is obviously the force. And when they say elongation, it's like how long is it being stretched? So it's a ratio. K is actually just a ratio. And you want to look, okay, so what does the slope of this graph represent? Remember, slope is the rise over the run. Change in y over change in x. Our y values represent the force. Not the force, but the force in the spring. And the x values are actually x. All right, it just works out that elongation is represented by x, and they're on the x-axis. Don't be confused by that. It's just the same variable. And what is f divided by x? Well, we just kind of derived it up above, I think, somewhere. Yep. This work here. I said, okay, f is equal to kx. Let's divide by x on both sides. Now we have f divided by x is equal to k. So K is just a ratio. It's where does this Newton per meter thing come from? It's a ratio of, okay, if I exert this much force, it's only going to stretch this much. What's the ratio there? That's the spring constant. So F divided by X is the spring constant. So that means that the slope is equal to the spring constant in an F versus X graph. So slope is equal to K. So the greater the slope, the steeper it is, the greater the spring constant is going to be. So which one has the steepest slope? Obviously, it's going to be A. I wouldn't want to be on this hill if I'm standing right here. I'm going to fall off this thing. That person has like 17 limbs, but that's fine. All right, I'm just showing that it's a steep slope. It's a high slope. So that means it's a great spring constant. Now, what does this mean? Let's look at this. Conceptually, I only went this far, but it took me so much force to only go that far. That must be a stiff spring. That must be a high spring constant. Whereas if I exert just this, I could get this far with D and only have to exert a small amount of force here. All right, so a small amount of force, it'll give me the same stretch. It must be a very loose spring. You could think of it like this. I could go all this way by exerting a minimal force. But in order to go this far for A, I would have to exert well, it's off the screen. All right, you'd have to exert a lot of force because it's a super stiff spring, and that's kind of what this graph represents. Okay, so number 7 says the graph to the right represents the relationship between the force applied to a spring and the elongation again. So it's F versus X graph. What is the spring constant? The spring constant is the slope, as we discussed in the previous problem. So we want to find the slope. The slope is equal to the rise over the run. Y2 minus Y1 over X2 minus X1. So the slope is equal to, let's find 2 points. Really, you could pick any ones. This one goes through the origin, so I always try to use that if it does go through the origin. Kind of makes the subtraction a little bit easier. So it could be anything. You could have chose the 16 one, could have chose the 8, could have chose the 4. I just went right in the middle there, kind of. Well, actually, this would be right in the middle, but anyway, 12 newtons, Y2 minus Y1, which we chose was the origin, 0 newtons, divided by X2, which is 0.6 meters, minus X1, again, is at the origin, so 0 meters. So you get 12 divided by 0.6, or 20. And what are the units we're talking about? Again, it's a newton divided by a meter. A newton per meter, which are the units for K. So K is equal to 20 newtons per meter. See, not only does it work out conceptually, as we were talking about before, but it also works out if you do the dimensional analysis, some unit analysis, you get a newton per meter. That's what the slope represents in a force versus elongation graph. Okay, number 8. 8 through 11, actually. Okay, so this is definitely a Regents question. And I just realized that my thing is a little bit off here. Hold on. That's better. Okay, it says, in a laboratory investigation, a student applied various downward forces to a vertical spring. The applied forces and the corresponding elongations of the spring from its equilibrium position are recorded in the data table below. So they tell you, it's basically this setup. You have a spring hanging from some fixed position, and initially there's no force being acted on it, but then you put a hanging mass on it, and it stretches the spring out. And the more mass there is, meaning the more downward force, the weight of each mass. As the mass increases, then the spring gets stretched further and further. So the variable they're changing, it's actually like a bigger mass every time. And a larger weight, therefore, because Fg is equal to mg. So the bigger the mass, the bigger the force due to gravity, and then the bigger the spring force. Before, it wasn't as big, and in here, Fs is equal to 0 newtons, as they show. So this is like the base case. You're not hanging any hanging masses. It's not being stretched at all. As soon as you put on a little mass, then it stretches out the spring, and this is the elongation of the spring here. It's all measured from the starting point. Now you're stretching it even further because you just put on more mass. So you can see it stretches further and further and further. Okay, now it says directions, construct a graph on the grid below, following the directions below. So it says here, first, you have to mark an appropriate scale on the axis labeled force. So we just have to figure out what the scale should be. You count up the number of lines, and you see what your maximum value is, and you have to fit it in. And they're actually not that nice to you because they give you 12 grid lines, and you need to get to 2.5 newtons. That's your maximum value. So what you do is you do 2.5 divided by 12, and that gives you 0.2083333. So if you tried to go up by 0.2 every time, you'd actually run out of room by one space because you could check to see if it would work. Point 2 times the 12 grid lines that we have, that better get you to the maximum amount, 2.5, but it doesn't. It's only 2.4. So at the very least, you'd have to go by point 0.3, I would say. You might try to get away with going by point 0.5 every grid line because, point 0.5 is kind of a nice number to work with. But watch what happens. If I do point 0.5 times 12, that'll give me a scale that goes up to 6. And I only need to go to 2.5. See, it would only take me 5 grid lines at that rate to go. So 5 grid lines is like 1, 2, 3, 4, 5. My maximum value would not even be halfway here. So for me, I like to stretch it out as much as possible with some reasonable numbers. Even though I'd like to use point 0.2, I'm going to go up by point 0.3. So really inconvenient numbers. They should have just given you one more grid line to work with here. If you wanted to take a shortcut, you could have just labeled the 1.5 and the 3.0 positions, but I have nothing better to do with my time, so I might as well just, make a nice graph here with all the lines labeled. So the first one you have is a force of 0 and elongation of 0. So we're starting at the origin. I might as well make it a different color. Okay. Now the next point is 0.5 and 0.01. That's our x value. So you go to 0.01, which is right here, and you go, because see, at first I was like, wait, is it over here or is it over here? Reading graphs, that you should know how to do this. And then it also gives you like this little line here. But a way to check yourself is, okay, how much before the next space? There's 2 spaces there, so this must have been 2 spaces, not the 1 space, even though the number was too big for the space and they should have made it horizontally aligned so there's no confusion, but they did their best to make it. Anyway, I'm getting off base here. So it's 0.01 and then 0.5 occurs around here. And you know what? I'm just realizing now that they want you to make a really squished graph because I'm not going to kill myself going to 0.5 is like 1/3 of the way between the lines. Again, that was me personally. I like to stretch it out if possible, but look at the numbers they give you. They're all 0.5. So I'm going to just make my life a little bit easier from that way, and I highly recommend going by 0.5 in this case. They should have just made it by 0.2, but anyway. Okay, question. You twisted my arm. I went up. Every line is 0.5. I took the shortcut and made just every other line 1. And now we're ready to graph again. So we have 0, 0. And we want to go to 0.01 and 0.5, which now is convenient to graph because it's right here. You graph the rest of the points like so. And it looks pretty linear. Just a side note, it's always nice when the graph works out and that's the only one where it's like 0.035 right on the line and 2 right on the line. A few things more satisfying than that in physics and science and just general life. I mean, when this happens, you just count your blessings. It's a very nice thing. Anyway, we said it was linear, right? So we're just going to draw, hey, this is like pretty good. Beautiful. That's some nice data right there. No, you spent all the time to plot these points. Yeah, it's not a perfect experiment. It might not be a perfect straight line, but the whole point is to draw the line of best fit, a straight line of best fit, because that shows your average data. So let's use a line tool or a straight edge or a ruler, side of a piece of paper, side of your folder, and you get something that looks like this guy right here. You could continue it if you want. You have your straight edge out. So just continue the line. Try to get it, that is a little bit too far up. See how this point here is hanging out by itself? Yeah, you could try to you don't want to point it. Some people go from the first point to the last point and just ignore everything else. That would kind of work in this case. I'd say it goes slightly above that though. The point is to try to get all the lines as close to all the points as close to the line as possible. That's decent. So it says, okay, plot the data points. We did that. Then it says draw the best fit line or curve. In this case, we wanted to do a line. And now it says what is the spring constant for this spring. All right, just like we did in the previous 2 problems, it's a force versus elongation graph, F versus X. So the slope represents K, again, because slope is the rise over the run. The Y values are the force. The X values are X, the elongation. So F over X is equal to K. So the slope is equal to K. So we're going to do some change in Y over change in X. So we have to choose 2 points that go through the line that are convenient. I like to use ones that are convenient to use, like not a big long decimals and some nice numbers. For example, I wouldn't use this point because it's not on like a grid line, and the grid line tells me what number it actually is. So obviously it goes through 0, so this is going to be our first point. And we want to find another point that's on the line that goes through what I call the crosshairs. All right, it has 2 lines from the graph, this guy and this guy, and that will be easy to extrapolate the data, meaning we're looking at this 0.035, that's the X value for 0.2, and 2.0, that's the Y value for 2. So you just do the slope is equal to y2 minus y1 over x2 minus x1. We chose 2 convenient points. So for y2, it would be 2 newtons. And y1 is 0 newtons. Divided by x2, we said was 0.035. It's in between that 0.03 and 0.04 meters minus 0 meters. So you get 2 divided by 0.035, which is about 57 newtons per meter. All right, that's about it. Have a good day. Actually, I ended the video there, but I forgot that I wanted to mention I could have, just started the video over when I made that mistake before. Remember that horribly embarrassing mistake where I didn't realize, I really should have realized that they were going up by 0.5 every single time, so I just should have done my graph by 0.5. I mean, it's pretty simple. I definitely overthought it, and it was just a stupid mistake. I mean, silly mistake. I mean, like, mistakes happen, people. And the reason I kept it in the video is to show you that I'm not perfect. Nobody's perfect. Everybody you know makes mistakes. And when you make a mistake, it is definitely okay. Do not be ashamed of your mistakes. You just have to learn from them. If you don't learn from your mistakes and you keep making the same mistakes over and over again, then you should be ashamed of yourself because you're not learning. That's the beauty about making mistakes and life in general, is that and for some things there's no second chances, but a lot of times don't make mountains out of molehills. If you make a little mistake here or there, that's fine. That's how you learn. If you ignore it and get embarrassed by your mistakes, then you're not going to get better. And that's all life is you're just trying to get better. And that's it. Have a good day.